Ok, bem-vindos, bem-vindas uma vez mais. E dessa vez a gente vai ter na audiência algumas pessoas que não entendem português. Então, por isso, tanto eu vou mudar agora daqui a pouquinho, quanto a palestra também vai ser em inglês, que eu acho que vai ser bom para todo mundo, né? É importante acostumar os ouvidos à língua internacional de ciência, mas fiquem super à vontade para perguntar em português. Tá? O Ugo está no Brasil há quase 4 anos, fala português mais ou menos do mesmo jeito que a maioria de nós, então fiquem super à vontade para interagir com ele na língua que vocês se sentirem mais à vontade. Quem preferir perguntar em espanhol, ele fala muito bem também. Quem preferir perguntar em italiano, obviamente. Então fiquem muito à vontade para aproveitar bem do Ugo.
Italiano, bem-vindo.
Exato. Então, antes de vou deixar o Marcos falar mais especificamente do Ugo, só vou lembrar que mês que vem a gente está planejando um dia especial para o último colóquio do ano, que vai coincidir com o primeiro jogo do Brasil na Copa do Mundo. Tá? Então a gente está pensando, ainda vai descobrir conforme possibilidades, se vai ser nesse horário que foi considerado usual por tanto tempo, embora seja não usual para vários outros aspectos, ou se vai ser um pouco mais cedo. Tá? Vocês vão ser avisados pelos canais usuais, de preferência até por mais canais do que os usuais, sobre a programação para daqui a 5 semanas. Mas para o ano que vem, a ideia é mudar o dia. A gente vai passar a fazer colóquios e algumas outras atividades em sextas-feiras. Mas isso também chegará à notícia no momento adequado. Beleza? Muito bom recebê-los. My pleasure to call Marcos Jardim to introduce.
Thanks, Marcelo. So it's a great pleasure for me to introduce Ugo Bruzzo. We've known each other for some 20 years. I'm lucky enough to count him as a friend. He is a professor at the International School for Advanced Studies, also known as CISA, in Trieste, Italy, since 1994. Nowadays, he's a professor of geometry and director for the Institute of Geometry and Physics in Trieste. But he also has a very strong link with Brazil. He was a visiting professor at Universidade Federal de Santa Catarina in 2015, and since 2019 he's been a visiting professor at Universidade Federal da Paraíba in João Pessoa. He has more than 130 published papers with 50 plus authors. His work is mostly in algebraic geometry, but always with strong interaction with mathematical physics. Also 2 published books, which are very nice books, by the way. One on supersymmetry and the other one more on algebraic geometry on Fourier branch.
I have 3 published books. You missed the last one. I have 3 published books.
Okay, so now there's a third. There's a third, we count.
And counting.
And counting. Yeah, more to come. He was also the chief editor of the Journal of Geometry and Physics for many years, from 2003 to 2017, and still active on the Journal of Geometry and Physics as a advisor. He's also an associate editor of the São Paulo Journal of Mathematical Sciences, that is edited by University. And finally, he's supervised 20 plus PhD students. Many of them came to IMECC as postdocs. There's one nowadays as a postdoc here. And also some of his students are also professors in Brazilian universities. I know at least 3. So his many years of interaction has made some significant contribution to mathematics in Brazil as well. So it's a pleasure to hear Professor Bruzzo to talk about McKay between algebraic geometry, differential geometry, and physics.
Thank you so much, Marcos, for this work. And actually, we know each other since 23 years.
Okay.
We met back in 1999, which is a statement about our age or anything. Also, I had 30 students.
Okay.
I don't know if
your CV on the internet is not up to date.
Okay. Okay, so thank you very much for this invitation. It's really a pleasure to be here again. I'd like to particularly to thank Marcelo and Marcos for the invitation. So it was a pleasure to be back at I got it. It's always a pleasure to be back at Unica. So I chose the topic, this is a colloquium talk, right? So I chose a topic which is kind of interdisciplinary between, well, inside mathematics, but interdisciplinary between among algebraic geometry, differential geometry, mathematical physics. Actually, probably in some algebraic geometry online talk, I already spoke of part of what I'm going to cover today. So it's not completely new, might not be completely new for somebody in the audience. So in case, please feel free to leave, no problem. And so what it is? So the title is, includes also the term McKay correspondence in particular. So what it is? So let me start with the classical McKay correspondence, which is about quotient singularities in complex dimension 2. So you have a finite group, which is actually inside the special linear group of order 2. And you have an action, and it happens that this action is free away from the origin. The origin, of course, is a fixed point, since the action is linear, and then the quotient is singular to the origin. Then you might like to do what in algebraic geometry, perhaps not only in algebraic geometry, but in particular in algebraic geometry, is called to resolve the singularities. The singularity in this case. That means to find another variety which is the same as the quotient, which I called x0 probably somewhere, anyway. So x is the resolution singularities, is isomorphic to the original variety if you remove the singularities. And replacing the singularity with something bigger is some clever way so that this new variety is regular, is smooth. So particular this new variety surface in this case is smooth, is away from the inverse image of the origin. The singular point is an isomorphism, and the origin has been replaced in this case by a subvariety which is a collection of copies of P1. Call it as you want, the Riemann sphere, the projective line. So this is an attempt to picture this, okay, in the drawing. So the origin is replaced by a kind of chain of balloons. And here something really amazing, if you want, happens, which is the following. The singularity, which means the subgroup, is related to some Lie algebras. The Lie algebras you may associate with the Lie algebra a diagram, which is called a Dinking diagram. And actually, the configuration of these complex lines, which is called the exceptional divisor, reproduces exactly the Dinking diagram. So this means the following. These singularities actually, well, first they have several names: simple surface singularities, Klein singularities, rational double points, Duval singularities. They've been widely studied and they received different names. And these are the, all of them using a suitable coordinate change can be recast in one of these forms. And so you see they have a name which immediately recalls a a Lie algebra. So in the case AN, and this is the case when the group G is given, the Lie algebra is this one, SLN plus 1C. The UN is related to the even orthogonal complex algebras. And then we have the exceptional cases where the Lie algebra is the same name, E6, E7, E8. These are the linking diagrams. And what happens is that you may think of these yellow small balls as the P1s in the resolution singularities, and the edges as the intersection points. So for instance, the first, if you like, is just another picture for this. Okay? This is basically the, so to say, in terms of pictures, is the McKay correspondence in two dimensions. This actually, of course, means something very precise from the mathematical viewpoint. In particular, what happens is that if you consider the second cohomology group of your resolution, it happens to be generated by the components of the exceptional divisor. So it is, in this case, it's generated by the cohomology classes of these spheres. And of course, since these spheres intersect in a very precise way, dictated by the singularity you are studying, what is called the intersection matrix of the second homology group is fixed. The way these classes intersect is fixed, and also actually the self-intersection happens to be always, well, the self-intersection happens to be -2, and the other intersections are either 1 if the sphere intersect or 0 if they don't. As a result, you have what is called the intersection matrix, which is this, right? This is exactly what I said. And you have this is the McKay correspondence, if you want, or another aspect of the McKay correspondence. This is exactly minus a matrix which is associated to the root system of the Lie algebras. Okay, so the matrix associated with the algebra. It is exactly the intersection matrix up to a sign of these generator of the cohomology of this resolution singularities. Very nice, great. I think I keep on, after so many years, I keep on thinking this is a beautiful result. It's a kind of miracle in a way, right? And actually, these spaces have been studied in differential geometry by Kronheimer, which goes, I mean, you have a problem now. How do we construct the resolution singularities? So a possible answer is in differential geometry by a construction which is called the hyperkähler quotient. This generalizes something which was already known in analytical mechanics or symplectic geometry, if you happen to know about it. This is called the Marsden-Weinstein quotient construction. And it's something that you use in mechanics when you have a system with a symmetry and you want to use the symmetry to reduce the number of degrees of freedom. And you can kind of generalize this to a general geometric setting, and in particular, you may like to do this when you have a hyperkähler space, perhaps a C2, right? And the group acts by hyperkähler diffeomorphisms, as it is the case here. And then, well, this action then it has a moment map, and what happens is that you can realize your desingularization as the inverse image. I mean, if for theta you put 0, you can prove U is a certain triple of functions, right? You take the inverse image of 0, so the 0 locus of these triple of functions, and you take a quotient by a suitable group. So this group is not the finite group G. This is a continuous group, a suitable continuous group. If you do this with 0, value 0 for theta, you get the singular quotient. You get the singular quotient. But if you perturb 0 with some generic value of this parameter theta, you get a desingularization, which happens to be hypercarry. Okay? And it has the structure I was telling you. In algebraic geometry, this corresponds to something which is called geometric invariant theory. Geometric invariant theory is the way to make quotients in algebraic geometry. Quotient for the action of a so-called reductive group acting on a scheme. In particular, you may apply the theory in this case, you get the same result. And this is, well, I don't think I will go now into the details of this slide. This is what I was telling you, waving my hands. Namely that you have some space and you have a map, which in this case is a triple of maps to the dual of the Lie algebra. You have this group acting on the space, also acting on the inverse image of an element in the center, the dual of the center of the Lie algebra, in particular 0, but not only. So, for instance, if you take the inverse image of 0, you can take the quotient by this group, you get a singular quotient, and if you perturb this a little bit, you get the singularization. This is what is written here, okay? This is the singular quotient, and if theta is a generic element in the center of G star, then, well, actually, not in the center, but in 3 copies in the center, then G acts freely in this inverse image, you take the quotient, and you get a resolution of singularities. And actually, in our case here, everything is hypercarrier, so the resolution of singularities is a hypercarrier manifold. Hypercarrier manifold means basically that this space has a family of complex structures, which is generated by 3 complex structures, which as endomorphisms of the tangent bundle are like the algebra of imaginary quaternions. And so, I mean, it's a real bidimensional family of complex structures which behave very nicely. Right? So it's a very strong structure for the math. And here I try to give an idea of what is the algebraic geometric construction, which is called the geometric invariant theory. Now, strictly speaking, the first sentence in this case doesn't make sense because I said use the holomorphic part of the moment map to cut a locus in the linear space where mu is defined. This doesn't make two, because none of these is holomorphic, but with the summary definition you can make, because you see there's the Michelin conjugate. But if you make the redefinition, you can make 2 of them holomorphic, and the remaining one real. So you just take the holomorphic part of it, and then if you just take the quotient of the 0 locus of this moment map, you get a singular quotient. And then in algebraic geometry, the trick now is to choose a subset, a subspace of the space you want to quotient. And this is obtained by fixing a so-called stability condition. So you choose a subspace. And this will depend basically on the same parameter. You complexify your group, you take the quotient, and you get something which, this is a theorem, is the same that you got in algebraic geometry. Or better to say, the algebraic variety you get as an analytical, an underlying analytical structure which gives something isomorphic to the differential geometric quotient. So the two constructions give the same result in this sense. Okay, now another actor is entering the scene because, can you speak clearly or no? Okay. What happens is the following. Must be very clear not to give you false hopes. What I'm going to say now only applies to the abelian case. Okay. It also applies to the other cases, but not in a straightforward way. You can reduce all these cases to locally, in some sense, to the abelian case, but it's a highly trivial procedure. So I will just talk about the abelian case. In this case, the desingularization can be done using toric geometry. Now I'll spend a few words to recommend all of you to study toric geometry if you did not already, because toric geometry is a beautiful topic where basically you are able to encode everything about a variety in a drawing. A very simple drawing, which is called the fan of the toric variety. You look at the fan and you understand everything of the toric variety. In some work, of course. You need to learn the theorems, how to, if you want to decode the information which is contained in this very simple combinatorial object which is called fan. For instance, well, E2 you may claim it's not so complicated, but this is really the simplest compact case. No? Look, this is a plain drawing. Don't look at it in perspective, because the colors might suggest to you that this is a simplex. No, it's in a plane. It's a two-dimensional thing. So the fan is made of cones, polyhedral cones. In this case, we have 7 cones. We have a 0-dimensional cone, which is the origin, 3 one-dimensional cones, which are these 3 half lines, and 3 two-dimensional cones, namely the areas of the real two-plane in between the rays. Let me call, as it is done, rays, the one-dimensional cones. So you have 3 of them. And actually, any of these corresponds, a cone corresponds to a subvariety of P2. The origin corresponds to what is called a torus in algebraic geometry, two-dimensional torus, so product of 2 copies of C star, and all of them are things of this structure, but of this kind, and they glue together to form P2. They glue in a form which is predicted by the fan. So if you look at the fan, you are able to find a number of open subsets, and the fan also tells you how to glue them, and the gluing turns out to be P2. Standard exercise in toric geometry. Also, the abelian A space. I forgot to say that the spaces constructed by resolution singularities constructed by Kronheimer are called asymptotically locally Euclidean spaces, shortened into ALE. So doesn't mean here, but it means asymptotically locally Euclidean spaces. Because they have a metric, I mean, the Kronheimer construction keeps them with a metric which at infinity, in a properly defined sense, is asymptotically Euclidean flat. Well, in this case, these resolution, these A spaces are, and this is a singularity, right? Because we are considering the abelian case, which in the two-dimensional case is just given by the groups, the cyclic groups, where Zn is a subgroup, realized as a subgroup of SL2C in this way. You see, N is fixed, and this is the generator of this group. Right. And already the singular quotient is a toric variety. The toric variety is given by this fan. It's a fan with the origin, which is always part of the fan, 2 rays, and one two-dimensional cone. This is the fan of C2 mod Zn. Okay. In particular, I made a particular case of Z2. This is not. This is singular. What is singular? There's a way. It's a theorem, of course, to see that this is singular because look. If you put these numbers 0, 1, 2, minus 1 in a matrix, you get a matrix whose determinant is minus 2. So it's not an invertible element of Z, and this means that the variety is singular. Which in more refined terms means that these two vectors are not the basis of Z2 over the integers. Okay. And then how to regularize this? There's a very nice recipe, which is the following. You should cut your cone in subcones in such a way that all of them correspond to a smooth variety. Meaning that the new cones are generated by a basis of Z2. And if you look here, if adding the red segment, the red vector, now this is true because, okay, this is that the yellow cone is just the first quadrant, so of course this is true, but also this is true because now this matrix, the matrix of these four things, has determinant minus 1. Which is good, because minus 1 is invertible in Z. And these two are basis, 1, 0, 2, minus 1 are the basis of Z2 over the integers. So the toric variety defined by this fan is good. Can you hear me now? Okay, you hear me now? Much better. Great. Okay, and then, okay, so this is our resolution of singularities. This is the first, if you want, the simplest of the Kronheimer spaces. In a algebraic geometric terminology, these resolutions are affine, and indeed they are represented just by one two-dimensional cone. This is no longer true for this. This means that this is obtained by gluing two affine varieties, but it is not affine anymore. And this is the case, for instance, of the spaces C2 mod Z4. You have to split the cone in more subcones, but you can always do that for every n. This is the picture for a simple exercise is that to check that all these cones, there are 4 of them in this case, they are actually smooth. They satisfy the criterion we were considering. And this is my remark that only the Alien space is of type A when the group is Zn are toric, because in that case the group G is abelian. Now, after a long introduction, because this was the McKay was something about the McKay correspondence to dimensions, and then I guess the question what happens in higher dimensions is very natural. So in particular, what happens in 3 dimensions? Now, this slide is about some preliminary material we need to deal with the 3-dimensional case. And here, this is a notion that in the 2-dimensional case is trivial. And this is the notion of age. Well, in general, you have a group which is non-abelian you split it into conjugacy classes, and then the age is an attribute of the conjugacy classes. Every conjugacy class is an age, which we are going to define. In the abelian case, conjugacy classes are just the elements of the group, right? So in this case, every element of the group has an age. And due to the fact that the dimension, G is inside the SLL3, the possible ages are 3, namely 0, 1, 2. Okay? 0 is just the identity, and then we have class elements. I think the idea comes from Miles Reed. I'm not completely sure, but I saw it for the first time in papers by Miles Reed. And this is the age is defined in this way, right? You just, for every element, you just take its eigenvalues. This is a matrix in 3x3 matrix. You compute the eigenvalues, and you write that since you are in the cell 3C, you can write them as powers of a primitive root of 1. And these powers they form up the age vector. Okay, the powers can be, the age vector is formed by the 3 numbers, and then you normalize by the order of the group. Okay, R is the order of the group, and then it's a small theorem that the age can only be 0, 1, 2, and you have 0 when the element is the origin. So here I said I write gamma E for the set of conjugacy classes of age I, but as I was saying, in the abelian case, this is just an example is an action of Z4. You see Z4 acting on Z3 in this way. I is the imaginary unit. This is an action of Z4. No, this map generates Z4. Then we have 4 elements that are 4 matrices in SL3. See, and I computed here the age vectors, and we see that, of course, we have the origin, and we have 2 junior classes and 1 senior class. Okay, 2 junior classes and 1 senior class. The last column, we are going to be back to it later. Then, what is this telling us about the desingularizations? Now this already happened in 2 dimensions, but in 2 dimensions something new, nothing special, but in 3 dimensions starts to be quite important. Namely, we call a resolution of singularity, which again, if we start from a singular variety X, is another variety which is isomorphic to the original variety away from the singularities, and it is smooth. But we also want something more, and this motivates the word crepant. And what we want is the following. Algebraic varieties come with an object which is called either the canonical divisor, let me call it a canonical divisor, which, when everything goes well, the canonical divisor corresponds to a line bundle, which is the bundle of holomorphic form of top degree. Here it's singular, the thing, so it's true, but it's what I said, but it's a little bit more controversial, so to say. But anyway, just to have an idea. The fact is that you want the pullback, you want the canonical bundle of the resolution to be the pullback of the canonical bundle downstairs, so to say, of the singular quotient, with no additional terms, because as I think we shall see in the next slide, there might be additional terms. We don't want additional terms. If this happens, we call it crepant. Why this is nice? One reason why this is nice, we are here in a moment. So again, the inverse image of the singularities of S happens to be in general reducible divisor. So it's a bunch of hypersurfaces, okay, that I call EI, each of them. In general, what happens is that the divisor of the resolution is the pullback. I changed the name of the resolution, sorry, from pi it became Zeph, but I mean the same. And additionally, you have some contributions which is given by the components of the exceptional divisor, so these irreducible hypersurfaces, each counted with a number, which is called the discrepancy of that component. And then here it's Miles Reed joke. Crepant is a back formation from discrepant. Okay, you take this away and you get crepant. Now for an Italian this is very nice. Because what does it mean, crepant? And crepant comes from the Latin. There was a verb, perhaps crepare, which means this, no? To crack, to creak, to rattle, to clatter, no? To make a noise of some kind. Now, this was classical Latin. What about modern usage? The standard meaning in Italian is that something cracks, like you know what you have you may have in a wall, a crack, no? And then you say il muro sta crepando, which means the wall is cracking. But in slang it means die. Crepare in Italian means is a slang for die. Crepante, I mean, is a slang for die. So what, for instance, the Brits call to kick the bucket. Okay, so these are varieties which kick the bucket. So this is what sounds to an Italian ear. Okay, of course, I don't know if Miles Reed knew about that, but anyway. And then we have a theorem which says that in 3 dimensions, for the direction of a finite group in a set 3C, you always have a crepant resolution singularities, which, however, may not be unique. In 2 dimensions, as we saw, just because this is life, you always have a crepant resolution, because hyperkähler varieties have a trivial canonical bundle, and these quotients always have trivial canonical bundle. So the 2-dimensional case always has crepant resolution that are unique. In 3 dimensions, they always exist, may not be unique. In 4 dimensions, may not exist. There are examples where they don't exist. The theorem was proved more or less by enumeration. Namely, there's a general theorem by Ito and Reed, but then there were cases left out, and they were studied by Rohn separately in Markuszewicz. So altogether, all cases are covered. The possible 3-dimensional, the possible finite group inside a set 3C are classified. There are a finite number of them. They've been classified by Yao and another Chinese guy. I don't remember the name. I think a former student of Yao. And then some family of cases were treated all together. And other cases, for instance, the Markuszewicz made the final example, a group of order 168. That was the last missing example. And then you see, what I wrote here, I drew here, and I said, okay, this may be said in a better way by saying that you have a relation between the Lie algebras associated with the singularity and the structure of the second homology group. Also exists in 3 dimensions, and this is a theorem proved by Ito and Reed. And namely, and here is where the age comes into play. Because what happens is that, for instance, if you consider the set of senior classes, they are in one-to-one correspondence with the compact components of the exceptional divisor. This is written a slightly different way using the term prime divisor, but it's the same. So you have a reducible component. The compact ones are in one-to-one correspondence with the senior classes. And then, okay, in homology, this means that they make up a basis not for the second homology, but for the second homology with compact supports. which is known to be dual by Poincare duality to H4 for varieties that are called perhaps Q manifolds, for which this theorem holds, and our manifolds are Q manifolds, whatever that means. I mean, we can apply Poincare duality. The same is true at the level of junior classes. In this case, the junior classes correspond to all components of the exceptional divisor. So they actually give a basis for the full second cohomology group, which on the other hand is dual to the fourth cohomology group with the compact coefficients. So for instance, if we go back to our table for Z4 with this action, we see, right, that we have, in total, we have two components of the exceptional divisor. One is compact and one is not compact. Why two? Because we have two junior classes. And one is compact because we have one senior class. So they are altogether, they are two, one compact, one non compact. And perhaps I made a drawing here. No, this is what, what happens in this case. One compact, one non-compact component. So these are the cohomology groups that we get in this case. Did I make a drawing? No, I did not. I'm sorry, because I had a nice drawing, but I didn't include it. Anyway, how to identify these divisors? What are they? No, they are surfaces in our three-dimensional variety. We want to identify them. And then we use toric geometry. First, there's a recipe. Toric geometry is full of recipes, which of course are theorems that you learn, and then you do things applying these recipes. And then there's a recipe. You start from the action, this action, and you construct a fan. You construct a fan which actually, since this quotient is affine, the fan will have one three-dimensional cone. You see, a two-dimensional cone in 2 dimensions, always has two generators. But as soon as you go to 3 dimensions, a cone may have more than 3 generators. A three-dimensional cone. 3 is the minimal number, then it's called simplicial, but it may have more. Just think a moment, you can think of something which is a cone, polyhedral cone, which 4 or more sides, edges. So this is what you get. Now this is in 3 dimensions, okay? These are 3 segments in 3 dimensions. And then again, if you form the matrix of the components of 3 vectors, the determinant is 4. It's not regular, rightly enough, because we know that this is singular. Actually, if you have a look at the, just by elementary geometry, you look at the singularities of this quotient, and you see that the quotient is singular at the origin, as always, but it's also singular along the z-axis. It also has a one-dimensional string of singularities, which is the z-axis. Okay, and then we want to regularize it, and then again what you do is that you split the cone into, let me say, minimal number of regular cones. And here, then I will say how you can guess what you have to do. What you have to do is to add 2 rays. These 2 rays, here they are red, they split the cone into 4 cones. And all of them are regular. I like to draw this thing that I call planar graphs, but they have another name, which you remember? No, they are not the polytopes of toric geometry. They have another nicer name, which I don't remember. So this is the original fan. I draw it as a triangle, simply because I have 3 points, and then I get a triangle. And then what we did here was to add 2 points. You see W3 and W2. And this splits the triangle into 4. And these 4 sub-triangles are the 4 cones here. How to find them? This is where toric geometry comes to its nicest. You do the following. Here, the blue points are Z3, okay, the points of Z3. The black arrows are these three rays, and then they are the vertices of a triangle, which is this yellow triangle. Here it has become gray, okay, this. And then you look for the points of the triangle which lies in the lattice, in Z3. I mean, they have integer components. And you get two of them, okay, in addition to the vertices that you already had. You get two of them, these are exactly these 2 points. And now, another nice thing is the following. W3 is inside, I should say that when you add a ray, you are adding a divisor, a hypersurface, and since W3 is internal to the triangle, this will be compact. And since this is on an edge, it is not compact. Of course, this seems to be magic, but these are theorems, of course, right? This is what happens. And of course, once you know the theorems, they make your life much easier because you can do things in this simple way. Sorry, I don't remember my slides too well. Little timing. Okay. I will write on the blackboard because apparently I didn't include a slide where the divisors were described. So we have the original fang. Perhaps this will be like this. Okay, and then we add the 2 new rays, this one and this one. So this was W2, and this was W3. Now, W2 corresponds, as I was saying, to a divisor. I mean, we added 2 rays, which means we added 2 divisors. These are the components of the exceptional divisor. What we added, we are replacing our singular locus with the 2 divisors. This, you make some computations, and you realize that it is this. And here what happens is that we had the z-axis, which is singular, and we replaced it with, so the z-axis is copy of C, and we replaced it with P1 times C. Okay, so the exceptional divisor, this component of the exceptional divisor projects onto this singular line. The other is something which resolves the origin. So it projects to the origin, projects under the map from the singularization to the singular quotient. No, this X is C3 mod Z4, right? So this is W3, and W3 must be a surface, and I'm not going to say much about that, but it's a surface well known to algebraic geometers, is called the second Hirzebruch surface. Okay, it's a surface. Second, and this is what the 2 here refers, because there's one of them for every natural number. Let me see what's coming. Let me see what time it is. Not much time left. An hour, right? At most an hour, right? Okay. to squeeze, to cut something. Again, you see here, I'm not going to the details, but again, I want to transmit the message that the desingularization can be done in two different ways. Again, using geometric invariant theory or differential geometric quotient, which is not going to be hyperkähler, at least because hyperkähler manifolds have even complex dimension. The real dimension is a multiple of 4. So in this case, it cannot be hyperkähler because we have 3 dimensions. But this is a Kähler, so the space is going to have less structure, it's just a Kähler manifold. The equivalence between the two constructions, and you see at the end of the story again, you get to some statement that you get the same space in the different categories, but they can be identified. The correspondence now is due to an Italian former student of Donaldson, whose name is Sardo Infirri, who wrote 3 papers, never with his stuff, never published them, and went to work in a bank in England, earning a lot of money and forgetting everything about the singularizing quotients. And they didn't even care to publish the paper, they just exist as reprints. Now, you see, now if you go back, for instance, here again we have this parameter theta. The theory says that this theta is an element in a space which is R to power, which is the order of the group -1. So in this case, in our case, 3. So it's an element in R3. And its role is to choose the stable points. Okay, to choose a subset such that when we take the quotient, we get a regular, a smooth variety, which is going to be the desired desingularization. Okay. Now, I said that not all resolutions are, in particular, not all crepant resolutions are the same. Where do we see different resolutions appearing, popping up in this construction? We see from the fact that you may say that you see, I have to say something. Sorry. I just spoke about stability, but there is also a notion of semi-stability. So basically, what I'm going to say is that if you consider our parameters theta, you may think to perturb them a little bit. Perhaps we don't need to talk about semi-stability. You perturb them a little bit, and then you ask, the resolution that I construct changes or not? Is the same up to isomorphism or not? And then what happens is that if you see that in this way the space of stability parameters is a disconnected subspace of R3, where each connected component is made by parameter such that if you move in this component, nothing changes. Okay, so the space of stability parameters is a disjoint union of these open components, which happen to be polyhedral cones. You prove that. They are again polyhedral cones. If you think that this has something to do with toric geometry, of course we are right. But we are not going to that now. So the idea is that you move inside one of these components, nothing happens. What happens if I change component? The answer is that it depends. Things may happen or not happen. It depends from the special situation. So we have this, you see, the space of stability parameters is a disjoint union of finitely many open convex polyhedral cones that are called chambers. And the wall is a codimension one face. Okay, so you have just to think, for instance, a two-dimensional case, not this one, not our guiding example, which is three-dimensional, but a two-dimensional case, no? The space of stability parameter is R2, and then it will be, you will have something like this, perhaps, no? In this case, you have three chambers and three walls. Now, there is a classification of walls. According to what? So, suppose you are inside the chamber and you move your point so that you hit a wall. And then you ask, what's happening? And then you can prove that moving on a wall may contract some components of the exceptional divisor. Or it may not. So, there are situations where from a chamber you go to a wall, nothing happens. You call this a wall of type 0. And then you have, what happens is that, what I said is just a special case. You may have a wall where divisors contract to curves. For instance, here, it might happen, no, that this divisor contracts back to C. Or you might have another case where curves, single curves, contract to points. A case is missing here, you might object. Why I didn't write that a wall of type 2 is when a divisor contracts to a point? I didn't write it because this never happens. This is a fact of life that you can motivate, of course, but so we have three kinds of walls. But anyway, what happens is that in this way, for instance, in our case, our space was R3, and we have, in this case, 8 chambers. Now, this is very nice, but very hard to read. But this is just to show off, because if you change the coordinates, the 8 chambers are the 8 octants of R3. So they are very easy to visualize. This isn't the original coordinates I was using at the beginning. It's quite hard to visualize. For instance, the bluish-green thing is a cone, clearly, and the vertex is the point away from you. So it's a cone which opens towards you. Okay? And you have 8 of them. Here the picture contains just 4. Right? And you have 8 walls among them. Each wall is a bidimensional cone. For instance, this one. This is a portion, of course. It's an infinite cone again. So this is the structure. What happens when you get to the... So, in our case, we made the analysis actually with the practical computation using Matemática software. I don't have time to explain how, but we did it in a very practical way. So we detected the position of the walls. And for instance, all walls, most walls are of type 0, 6 of them, if I remember well. 2 are of type 3. And type 3 is very easy to depict. You see, here we constructed the complete desingularization. But what about if we add just one ray? We might like to introduce only, for instance, W3. Why not? The result is that now, here we have one cone singular. Now, just adding only W3, we get some cones are regular, some cones are not. And actually what happens is that we get another space. It's no longer, well, I didn't say that, but the space that we get in this case is the total space of the canonical bundle of the second Hilbert surface. Okay, it's a line bundle over this famous second Hilbert surface. Anyway, whatever it is, if we only explode, so to say, W3, so now we have only this inner point, no? We are not considering W2, which was here. The result is that we just have one compact component. So the exceptional divisor only has one component, and it is compact. You compute it, toric geometry again helps you, and you realize that something which is called the weighted projective space P112. You see, this here seems the usual projective space that we know from very early in our academic career, but with the difference that the action is not the same on all coordinates. The action is given in 3 dimensions, and then the result is 2-dimensional, of course, by a triple of weights. So you see, in particular, on the z-axis, z-coordinate, we act with lambda squared. The result is something singular. This has a singularity in one point, these two spaces. And then the total space of the canonical bundle of it is the toric variety corresponding to this fan with only 4 rays. And then going back to our walls and chambers, what happened was that going to one of these walls of type 3, we contracted this divisor. We contracted it back to its original form when there was a singularity. This singularity is a line, and this space is singular along a line because this weighted projective plane is singular to one point, and this is a line bundle on it, and the whole fiber over that point is a singular locus. Right? So we have the singularity of lines, which has not been resolved. No? The z-axis which has not been resolved. Now, I forgot to say that, of course, well, Marco said that. No, Marcelo, you did it so far, but you can stop me at any time. It's a little late to say that, but anyway, to ask questions in any language you want that I can understand. And this is particular I'm going to slightly change the topic because the title was, if you remember, McKay between algebraic geometry, differential geometry, and physics. So what about physics? So let's spend the last few minutes about that. I'm not going to the details because first we are not physicists, second we don't have time. But what is very interesting? You know, this happens a lot in modern mathematical physics. For instance, in string theory, in supersymmetry, it happens that mathematicians and physicists work on their stuff. At some point, they realized they were working on the same stuff. And then, let me see what I can. You see, I will be back to this because I want to have a look to the previous slide. But here we have a dictionary between geometry and physics. And what's interesting is that the two communities introduces this stuff independently. At some point they realized that people were talking about the same stuff. Okay? And as usual, you know, a dictionary takes a concept and tells you how to express the concept in a different languages. Usually you understand well a language and not the other. And this is the usefulness of a dictionary, of course. Right? So now we are exactly in that case because we can more or less understand, especially we can understand the left column, we are not going to understand much the right column, unless you know quantum field theory and all of that. But this is the idea, right? That there's a full correspondence between geometry and physics. Again, as it happens, for instance, in string theory, all this stuff actually is related to string theory. Now, the varieties we are talking about, the geometric structures we are talking about from the physical viewpoint are related to supersymmetry. I'm not going into any detail about this, but you might know that in physics you have particles that are called bosons and particles that are called fermions. And usually in physics, before supersymmetry, the two categories of particles were very independent. They didn't want to mix each other. Then we have symmetries, space-time symmetries like the Lorentz-Poincare group, change of reference system basically. And we have also other symmetries which in modern physics are used to describe the fundamental interactions like electrodynamics or the strong interaction in nuclear physics or whatever, but the particles never, of the two families, they never mix one with the others. Supersymmetry does that. It mixes bosons. Here the boson is phi with the fermions. Here the fermion is a psi. From the mathematical viewpoint, phi is a scalar field, is a function, while psi is a spinor, is a section of a vector bundle with some special properties. You want a theory which has this kind of symmetry, then there are some, you want to quantize it, and then you discover that unless you go into 10 dimensions, the quantum theory is not consistent. And then you say, okay, let's go to 10 dimensions. But we know that we live in 4 dimensions. And then the idea is that you think that the manifold of the theory splits, for instance, as a product of something which is the physical universe we see, V4, plus something which now is real 6-dimensional, which is called internal manifold. What is super interesting is that the physical structure of the theory tells you things about the internal manifold. It tells you it's Calabi-Yau, it's scalar. It has a lot of interesting structures. So the physics is encoded, part of the physics at least, is encoded into the geometric structure of this internal manifold. So the idea is that at any given point in space-time, on top of an event, there's an internal manifold which is compact. It is so tiny that to see it, you need a tremendous energies, and we usually don't see it. You see the last sentence here, the physical model dictates the geometry of the internal manifold. I believe this is a beautiful part of modern mathematical physics. And here you see, we have an example. Let me just take it as an example. It's like, it's like to have a dictionary between Portuguese and Russian. I don't know if somebody speaks Russian here. Nobody. So we wouldn't understand the Russian words. Okay? But you see, I'm just advertising, so to say, the fact that basically every object we used has a different name in physics because it is an ingredient in a quantum field theory. So, for instance, the elements here are the values of the so-called West-Zumino fields. This group, if you might remember that we wrote that, for instance, doing the Kähler differential geometric quotient, is the so-called the gauge group of the Chern-Simons theory. We introduced the moment map. These are functions known to physicists. The stability parameter, they were introduced in physics in the 70s by these two physicists. They are called Fayet-Yiannopoulos parameters. The quadratic constraint, I didn't talk about that, but it's called the potential by physicists. And then you see that their last line sounds very, very well. No? Because the minimal Krepan resolution that we constructed, it's really minimal. I didn't define what it means, but I mean, it's a minimal in an intuitive way, in the sense that it's the smallest space that you can introduce to resolve the singularity. Here it's the manifold of classical backward. So the quantum theory has some kind of a fundamental state with minimum of the energy, and these states don't come isolated, they come in families. They are called modular spaces also by physicists. They describe the possible solution of minimal energy of the classical theory. And they are exactly our Crepin resolution. Okay, this is just, I understand just hand waving, but I think that they at least transmit the message that everything we do in geometry often as a counterpart in physics, and of course to study the interaction between the two worlds is something which is very interesting and productive, of course, because not only the physicists, as they used to do for many years, they use mathematics to do their computation, but their techniques can suggest new avenues in mathematics, new theorems, new proofs, as it happened regularly over the last 50 years, and Fields Medal were given for that reason. So it's a really fascinating part of mathematics. So thank you very much. Probably.
But 2 o'clock should be after the questions.
Sorry.
No problem. Questions? Dubidas? You don't even, okay, you have one there, but I would like to ask where to start studying toric geometry.
Say it again.
Where should we start studying?
Study?
Yes. Give a book or something.
Sure. Cox a little shake. It's the gospel of toric geometry.
Okay, well, the first question is related to something like I don't like too much in right this business of negative intersection. Now in the spot, I would
You
like
always
to
tell me
ask
that.
you.
I know William since
In the
7
spot-
years. You always tell me this.
Yeah, it's something that it's still like like
Okay.
7 years.
I will give you
studying.
the usual answer.
Okay. In
I
the
don't
spot,
have
I
to
was
give you
expecting
answer,
that
but-
maybe you.
No. You want an answer? No, simply
Okay.
when it's.
But you understand that it's difficult to digest that business, right?
No,
Like,
there's
that's
nothing to
something-
digest.
No? It's like intersection, negative intersection?
Sure, there's nothing to digest. Because you are too much constrained by the name. Because a negative self-intersection is not an intersection in the sense you think. Because what happens is the following. That if you have, for instance, inside the surface, you have 2 lines which intersect transversely very nicely. Then each line gives you a cohomology class, and there's a recipe to do this computation in cohomology. So the number of intersection points is something that you do in cohomology. Okay? This is a theorem. If the 2 curves intersect transversally, then the number of intersection points is computable in cohomology. Now, if the 2 curves coincide, this is the definition, because this makes sense also in that case. Then you can interpret this. Because, for instance, when the self-intersection is negative, you take the curve, no? C squared is negative. You take the curve, you try to move it, you cannot. As a consequence of this, because this is related to geometric features. The normal bundle has no global sections, so you cannot infinitesimally move the curve. That's it. I know I didn't convince you today a lot of times. So.
It's like, as far as I know, it's very difficult to produce hyperkähler manifolds. And so how do you...
Compact ones. They are very difficult to.
Okay, with regard...
The non-compact, I mean,
But so how you have a machine to produce hypercase?
well, but it was a two-dimensional case. These are the Kronheimer Ailey spaces, very well known. But in any case, what is very difficult is to construct compact hypercare.
Another question is like when you describe, you don't get toric manifolds, but you expect maybe it could be a more infinite space or something like
You
that?
mean the non-abelian case?
Yeah.
Not even the space you start from is toric.
So you singularize and you go away.
No. If it is toric, the desingularization in this case is toric.
Okay.
The non-abelian case, not even the quotient is toric.
But
But,
you expect it could be more in...
Probably it is, but I don't know. What happens in that case is that it may be realized as a patch of toric varieties whose patching is not toric. Then each of them can be resolved, and then you can do things. And this is the Ito's paper. They do it like that.
Thank you.
It's a non-toric variety made up of toric varieties. Then you use that value.
Okay, before thanking Ugo again, let me remind you that he will still be here tomorrow, and there is a seminar, I believe, 3 p.m. or something like this. If anyone is interested, please ask him. And that we have another event here. Some people must be here because of this. Sorry for those. And let's thank Ugo again.
Thank you very much.